All right. So thanks everyone for having me. Just real quick before we get into it, just trying to give you my background. I started life back in 1999 in the industry as sort of a pure power electronics hardware designer. So just doing a lot of like MOSFET and IGBT stuff for real high power distribution systems. But it pretty quickly led me into motion control stuff, and also power systems that had DSP involved in them. And so I started getting more involved in embedded firmware, and really fell in love with it. So I've sort of been doing that ever since. So I basically, as an embedded engineer, I'm riding the line between electrical and firmware. So I design all my circuits myself still, but then I also end up writing the firmware for them, sort of end-to-end system level thing. So as I said, I did some motion control and manipulation stuff. I've done a lot of embedded custom sensor stuff, miniaturizing things, very small packaging, power distribution, and just generally robotics stuff. So you'll probably recognize at least one of these photos on the right here, which is Ariel's project. We also, the company I was at previous to this, down in the bottom right, I was working on the commercialized version of Professor Hugh Herr's bionic ankle. Spent a little time at iRobot, and also did some EOD robots at Foster Miller back in the day. By the way, jump in anytime with questions. I always like to start with this because as cliche as it is, it really is true that you can only get two of these. Good, fast, and cheap. Looking at it a little less cynically, you can look at this as the quality pyramid. So scope, schedule, and resources, which is like a little kinder way to look at it. But this is also kind of a nice way to look at it, as more of an intersection of different qualities that you can get. Obviously, for the kind of stuff that you guys are after, you have one flight to make it happen, several parabolas within the flight, but once you're on the plane, the thing has got to work. So the good is sort of the primary concern. Fast and cheap are nice to have. Obviously, you want to iterate quickly and not go crazy over budget. Fortunately, in my career has been interesting in that even when I was at large companies like iRobot, I was still sort of on the R&D side of things. So I've spent a large portion of my career just quickly building and iterating on prototypes. So that's kind of what I hope to talk about here, and kind of help you guys get off the ground, pun intended. So you have an idea, you want to make a thing. How do you go about it? So I've sort of broken this up into like how I think of it as, first of all, this is design and development, actually going through the process of defining what it is, how it works, and how you're going to get there. So I'm going to touch on each of these items. There's also the consideration of the unique environment of being on this flight, on the zero-G flight, and the thing that you build needs to operate properly in that environment. So we're also going to talk a little bit about what does it mean to have something flight ready. So in thinking about what to present to you guys, I was thinking about electronics in general in the zero-G environment and how they behave. Fortunately, actually, a lot of the things, the way they behave on the ground is the same way they behave up in the air. Things like microcontrollers and small motors and stuff is sort of, you can just treat them the same way. But there are a few notable exceptions. Of course, IMUs, which is inertial measurement unit, for those who are not familiar with that acronym. Obviously, when you're in zero-G, things like accelerometers and gyros they're going to behave a little differently, especially I would say accelerometers, because a lot of accelerometer manufacturers actually try to compensate for gravity in some way. And certainly I would imagine there are accelerometers out there that are geared towards space flight, but you're not going to be able to find them on SparkFun. So the kind of stuff that you're going to buy for a couple bucks on accelerometers and IMUs, they're not really made for that. Not to say that they can't be used. It might actually give you some really rich and interesting information to look at how these things behave in zero-G. But just something to keep in mind. Also, as far as magnetometers go, I haven't actually tried these in an aircraft, but being surrounded on all sides by metal is probably not the best thing for a magnetometer or gyro, or sorry, compass. The other thing to think about is like barometers. The flight is a controlled environment, but like, as everybody knows, has been on a flight, like your ears pop as you're climbing to altitude, and as far as like temp and humidity, if you're on a flight for 6 hours, you're drinking water constantly because the air is so dry. So it is a controlled environment, but not probably controlled in any way that is super predictable, I would say. But interestingly, if your experiment depends on those things, you might actually depend on these sensors to tell you that what the temperature and humidity were, and what the sort of air pressure was like. It all just depends. So, generally, I just wanted to point out that like sensors are pretty stable things for zero-G flight, but just sort of give it some upfront thought and kind of run some thought experiments about what might be different with those. So timeline, as I mentioned, I've done a lot of prototyping on sort of short time scales myself, and you guys are sort of in this arena, right? You have 1 semester to go from whiteboard sketches to a flight ready thing. There's a lot that needs to happen. So I'm just going to sort of talk about my experience in planning and executing these kinds of things. And one of these things is modularity. So you basically want to think about like, how can you break this down? Assuming that you're going to have this sort of electronics and code together. Obviously, that's where I'm coming from. So I'll focus on that. But you need to sort of think about how you're going to pull things apart and break them down into testable chunks. This can be isolating the electronics by themselves. This can be isolating small functions of the electronics in the code. And with a goal of moving towards the complete system, but finding milestones along the way where you can put a pin in it and say like, okay, well, it might not be the whole thing, but it's 85% of what I wanted, like trying to find this linear progression of functionality and completedness. So in practice, sorry, I don't know if the faces are covering up. I guess you can move them around a little bit. Just covering up a little bit of the text on mine, but that's okay. In practice, like the way I would think of breaking things down is like sensors. We sort of hit on this already, but what are you sensing and how are you going to do it? What's the minimum number that you can get away with? I've heard the phrase to simplify things as much as possible, but no simpler. There is the risk of oversimplification, which will get you in just as much trouble as overcomplicating things. The low-level requirements of the sensor are the next thing to think about. Like, so I use the example of a TOF sensor here. If you look at TOF sensors nowadays, time of flight, you will see that there are dozens and dozens of them available from a lot of different vendors that specialize in different things and hit different price points and range and field of view, and there's all these kind of things. So trying to figure out up front what your real sensor requirements are, I think is important. You need to sort of hone in on that earlier rather than later. Getting a broad picture is fine, but pretty quickly you're going to want to actually be talking to a sensor, pulling data off of it, and seeing if it's really, accomplishing what you're trying to accomplish. And so to do that, you need to dig a little deeper, sort of, not immediately, but front load that a little bit. Picking a processor, similar sort of thing. You need to think about the number of IOs, the analog signals, the comms, which ties directly into typically what sensors you have chosen. And I've said here, like, generally the dev boards these days, Arduinos and the Teensies and the Nucleos of the world, are very diverse in their. They have just like a rich set of generic outputs, but it's something you need to look at. Power requirements. This is one that I think is often glossed over and can be a little dangerous. Maybe not physically, although maybe that too. But I think there's not enough thought put into the power requirements as far as power domains needed, different voltages for different sensors and for different applications, battery life, current, like how much current things are drawing, how much, the sort of type of wire you need to carry that current. So this is another one that's can be sort of like broken off into its own thing. You can sort of make a power budget and just figure out, like, okay, how am I going to power this thing for half an hour, 45 minutes, or however long the flight is, and do it safely too. And we'll touch a little bit more on safety later on in this presentation. So as far as the code goes, there's a question of comms again. A lot of people, the comms can be pretty well abstracted these days. Again, like using things like Arduino, they make I2C very easy, and they make UARTs very easy, and SPI sort of easy. Maybe not quite as easy as the other two, but there is a lot of some thought needs to be given into how the comms are happening, when they're happening, comms to the outside world versus comms within your system. The sensor bus versus the storing the data or communicating to the outside world. And this sort of ties into the next one, the program flow of the state machine. What needs to be controlled all the time? What should be pulled? What should be interrupt based? And if you do have a state machine, or you have some sort of interrupt based or real-time operating system, it's important to try to find a way to exercise all the paths through the state machine. This can be especially interesting, as the state machine grows. It becomes harder to do, obviously, but then you end up with more corner cases, and trying to find out how you can get into those corner cases, or how to avoid code lockup or defaulting states, stuff like this. This sort of ties into the not just the functionality of the program, not just the ability to promise to yourself and to the flight crew that it's going to work safely, but also to convince yourself that it's that it's going to accomplish your mission and get you, which leads into my next thing, data collection and storage. You want to obviously get a very rich data set. You know, the parabolas are short, 30 seconds or so, I believe, and you get 20 of them. And in that time, you know, that's 10 total minutes of testing time. So you need to really think about, like, what is all the data I can possibly get, but, you know, format it in such a way that you can use it afterwards, thought through in such a way that it will make sense. So again, you know, these are just sort of like the my sort of standard beginning the project principles that I'm presenting here. I see stuff coming across the chat. Sorry. Well, maybe not. Sorry. So one thing I love to harp on, because I think it is so important, is buildability and reliability. You know, and I use the example here of you know, these Molex Sherlock connectors. It's a nice secure little connector that you can buy for relatively cheap. The crimper, the hand crimper, is quite expensive, but actually compared to most crimpers, that's not even that bad. They can easily reach into the thousands of dollars. But the thing is, and I actually do this all the time still, you can buy these pre-crimped wires from DigiKey. You can buy actually fully populated connectors, which are perfect. If just going through the years and through my experience, you know, the number one item that's going to cause you problems on rapid prototyping is electrical interconnect. These things fail, you know, easily under stress, to put it that way. And just spending a little, you know, a little time up front on thinking about, like, how are we going to connectorize this thing? How are we going to protect it? You know, I'm going to go back into this again. But I can give a quick example, actually. It sort of touches on a couple of things that I've said. Actually, I'll say that for a second. But, you know, this is just something that you really, for any electrical system, the reliability of the connections will literally make or break the experiment. You know, another example. Oops, went too far there. Another example of sort of buildability is using these dev kits, these off-the-shelf dev kits. This is, you know, probably a lot of you are already familiar with this, so I won't spend too much time looking at it, but just wanted to point out that there is still like a trade-off with this. You know, I'm giving the example here of measuring temperature. You know, we could build an op-amp circuit that would do that, or we could just buy this, you know, one of these sensors from Adafruit that will also do the same thing. So what's the trade-off of that? Well, like the Adafruit part is going to be pretty well vetted. It's going to be, you know, debugged and working. So it's just something you can just buy and just plug into your system and start right away. But then it's going to add some communications overhead. So you've traded off the simplicity of the circuit design for the communications overhead, and also potentially giving you a little bit of overkill from what you're actually trying to measure, because these things are made to be extremely general, right? Same thing with the dev kits, microcontroller dev kits, the Arduinos. They're made to be very, very general. So you can sacrifice something potentially in what you're actually trying to measure by, you know, by measuring a wide range when you actually are concerned with a narrow range. You'd rather have very high resolution on a narrow range than average resolution on a wide range. So these are the kind of, you know, the trade-offs that you want to sort of think about early on. But getting started with something like this is great, because now you can just plug this into your system and you can get some data rather than, you know, waiting to design a circuit. And this is where I was going to say, like, this board that I'm working on now, this board that we designed It doesn't really matter what it is. I just wanted to point out, like, this is a fully integrated design that does a whole bunch of cool stuff. It actually started out life as just this, a Nucleo board. We just bought it off of DigiKey, STM32 Nucleo board, and we ran this with this for weeks and weeks, just soldering stuff right onto the pins. You know, and this is destined to be like we hope a pretty legit robotic system. And started life as a Nucleo board. We then took the interim step, as you know, as I was saying, like electrical connection reliability is an issue, and soldering wires directly to this board proved to be pretty problematic because they would break off easily. So we took sort of a interim step. I don't know, it's hard to see this, but this is just a simple 2-layer carrier board for the Nucleo that has a bunch of IDC headers on it, and so now we can make really secure ribbon cable connections, which we just build up a bunch of cables for all the different peripherals on ribbon cables, and we affectionately named this the Genie Roadkill because when it's all laid out with all the wires going every which way, it looks like it got hit by a truck. But so this is a, you know, just some advice I would give. We did the same thing with an FPGA board. We just made little dongles for, this is another, just an off-the-shelf dev kit for an FPGA. You can kind of get your system up and running quickly in this roadkill fashion. What's called, it's kind of a, the term of art for building these systems that are just splayed open, not particularly compact, probably not the final form factor that you want, but they will get you started quickly, and you can figure out if you want to spin it up into an actual board at some point. But you know, I wanted to point out this one. This obviously is Ariel's project, which Ariel and I and Pete worked on for sending up to the space station. This was an extremely miniaturized 6-layer rigid flex board. You can see these are on little rigid arms, flexible arms rather, that fit inside the carrier. This was a really cool thing to design and build. And it was like very satisfying the first time we saw these come out of the fab, and then yeah. But this is like sort of a monumental effort, you know. So this is like it's great to aim for this, but like just don't put something like this on your critical path, you know, because
that board, to Jamie's point, was the result of 2 years of incremental development towards that final flight design, the first of which was designed for a zero gravity flight, the second of which, like the second big version, was for a suborbital flight with Blue Origin, and then we miniaturized, and with a bunch of Jamie's help and another collaborator, then got it down into this kind of ultimate form factor for the ISS flight. But it was a lot of iterative steps going into that.
Mm-hmm. And actually, I should have grabbed the other one that actually flew on 0G. Well, the Blue Origin ones, did they also go on 0G? They might have.
That's right. That summer we took the second version and flew it on a second parabolic flight because we happened to be ready from the suborbital flight that had ironically happened before in May.
Yeah. So yeah, I'm happy to help with these kind of designs. You know, like I said, it's very gratifying when you go from a bunch of wires and dev kits, and then you know end up with a beautifully laid out board that comes from the fab with all the connections just right, and it's definitely something to strive for. So, but you can also do a lot with just stringing things together and actually get a lot of meaningful prototype and meaningful data for your experiment. So I did want to touch a little bit on Failsafe. I made the general blanket statement that the most electronics on zero G will be low energy, but I guess I don't really know that because I'm not familiar with the projects that you all are building at the moment. But depending on the level of energy, even if it's low energy, if you're flying like lithium batteries, if you're storing a lot of energy in a cap for some reason, we've done that before certainly. You need to have sort of a good answer around why that's okay, why that's safe. Another good example of it is we on the ISS, a couple of experiments flew Geiger counters, and the Geiger counters had or have, in fact, I think that you might be working on these kits. No, no. Okay, that didn't materialize. But anyways, they have a high voltage node. It's actually pretty safe. It's the kind of high voltage that if you touch it, it would be like touching a doorknob in the winter. It would zap you, but it wouldn't really hurt you. But high voltage is high voltage, so we needed to you just write up a little test report saying, okay, we tested it this way, we conformally coded it, we measured the impedance between the high voltage node and all the touch points that were accessible. So things like that, if you're running some sort of energy storage or high power flow, even if it's like brief, like pulse power, you just want to think about, okay, if a wire breaks, if the power is flowing and a wire breaks, like where's that going to go? It's going to cause a voltage spike somewhere from the inductance. So how can we figure out what that is? This is going to be like towards the end of your experiment, probably, or towards the end of the prototype cycle when you're getting ready to fly. This is the kind of like the last few things that you're going to want to think about. And you also want to think about how can you recover if these things happen. As far as data collection, we want to automate this. You want to think about automating this so that you don't have to interact too much. Having said that, I understand that many of the zero-G experiments may actually be about interaction, but the data collection behind the scenes can be something else, right? So I give this example here. This was for Valentina Semina's Space Human, which was a pneumatic tail with, you could inflate different chambers to create different shapes. Some of you may have seen it. I should have included a shot of it here, but this is the guts of it. So what you're seeing here in the lower corner is a big an array of pumps. Next to that is a little control interface. Then there's an array of valves up in the top right, and then there's a teensy with more ribbon cables. I love the ribbon cables; they're so easy. But what this did is like we had one LED, that's actually a red and green LED in one package. So it would blink for the sequence that you were on, for the parabola. It would blink twice for parabola number 2. So you could easily just look at it and see like 1, 2, pause, 1, 2, pause. Okay, it's on parabola number 2. The black button was to change the sequence. So if something got out of sequence, you could cycle through and get back to the sequence that you wanted to get to. The white button was to lock it. So you hit the white button, the LED is still blinking the sequence, but it turns from green to red, indicating that that's now locked in and ready to execute. And then the red button executes. That would actually, start the pump sequence for whatever, there was different combinations of pumps and valves for the particular parabola and type of shape that Valentina was trying to create with the tail. So this is an example of like we were trying to like absolutely simplify it. So it's 3 buttons. There's a 2-button sequence to fire it, so you can't accidentally fire. I mean, I guess it's theoretically possible, but it was like you had to go 1, 2 to first lock it, then fire it. So this is sort of an attempt at both simplification and fail-safing, so that it was easy to use quick to arm and fire, but also required two actions in order to make it happen, so that the experiment couldn't go off prematurely, or was less likely to. On the right there, we see this was just totally automated. As soon as you push the button, it started writing this to an SD card, sequence to the target gravity. The pumps and valves is just 1 for on and 0 for not. And then these sensors, these were like flexible sensors. So this is the raw ADC value. So we had a script that after the fact would turn these into meaningful data. This is just like raw ADC information. But this is something we came up with. It was just, we thought it was like pretty simple, pretty clean, and very automated in terms of actually collecting the data. So she could just concentrate on like getting into position, because this was like a very like physical interaction type of device. She didn't have a lot of time to be taking notes, so to speak. So it was all just written to an SD card, and we parsed it, after it was back on the ground.
Just one quick note that I'll jump in to mention about the buttons and the design of this framework. I think it was super helpful for Jamie to have built up this method for Valentina to interact and control the, kind of overall goals for the payload in flight. We had a student the very first year in 2017 try to do something similar with a safety backup. Zero G had said for all systems, you have to have an emergency shutdown. So you have to be really able to quickly cut power. So this student very diligently hooked up an emergency red stop button, like what you see in a shop, that basically just cut power quickly to his entire experiment. His experiment was a series of syringes that were trying to do additive manufacturing in zero gravity, essentially, and doing UV quick flash curing of resins. And unfortunately, he didn't cover the emergency stop button, and somebody kicked it during flight, because we were all flailing around a little bit more than we're used to. And unfortunately, that cut to power happened at precisely the worst moment, and his resin was cured while still in the tubes and blocked his syringes for the remainder of the flight. So then he was trying to, force it through manually, and just caused a lot of trouble for him. So a meta point is, if you are going to have buttons like this or a system like this, also think about a cover or simple human factors things to make sure that you're less likely to make a mistake with the buttons, or for somebody else to bump into them or make a mistake with them. Just a quick comment that, we sometimes remember to, tell people flight to flight based on that student's experience. And sorry, Jamie, for interrupting. Please continue.
That's a good point. Yeah, it actually kind of ties into this a little bit, because you can see here that, just jumping to the third bullet point, similar, not quite like that, but we also, Valentina had a failure mid-flight. I think she got through 2/3 of the parabolas about, but when she came down on the system, like when gravity resumed, and the USB connector that like physically soldered to the Teensy device just pulled right off, because it's just not a strong soldering joint. So that was a sort of a hard lesson to learn in the middle of a flight as well, because she was basically done at that point, though. I mean, the thing was, just, connector was broken off, and there was no way to fix that. So you do want to also, it was a good segue, because I was going to talk about, like, you need to think about, like, can you build a backup system? Can you fix things in flight? Can you take spare cables or spare batteries? That may not be allowed, but something to think about. And of course, like project boxes and standoffs within the project boxes, heat shrinking things, strain relief of cables, again, with the electrical connections, just soldering directly to a board. If you're going to solder, like butt joint solder into a board, you really need to like make a little service loop and then zip tie that to something, or just think about, like, okay, if someone were to pick this thing up and just like shake it like this, like what would happen? Would it be okay? You need to make sure that the answer to that is yes. So I'd like to finish with one of my favorite quotes. My brother and my wife are both librarians, so but I really believe in this. I am sort of a believer in struggle. I think like fighting through a problem is a good thing, but also at some point, it just leads to frustration and not answers. And you know, that's why we are here, to help you out with this thing. At this point, I've read literally thousands of pages of data sheets and technical reference manuals. I've spun a ton of boards and I've made a ton of mistakes, and figured out a way out of them. So, you know, if you have questions along any of this kind of stuff, PCB design, circuit design, if you want to help reviewing components, picking sensors, you know, please feel free to reach out. And I will cede my time to Pete, unless there are anyone that wants to ask any questions.